that certain 2 week or 2+ some this 2+ week is there where we can discuss certain topic. So so far regarding this discrete mathematics, whatever we have discussed, module 1, module 2 and module 3 before that term exam we started discussing about module 3 corresponding counting technique. And one more thing is there from that counting technique, that is actually advanced counting technique. So that will start today, and we'll continue that in the next class as well. So next class probably will get in the November. So far regarding this subject corresponding syllabus, two things are left over there. One is advanced counting technique that will start today. Another is graph corresponding few concepts. Fine. So that is that comes under the module 4 corresponding. So today I will start the advanced counting technique that is there in the module 3, and after that module 3 it will be completed, and then we'll switch to the module 4 where graph corresponding certain thing we will discuss. Fine. So regarding that midterm exam, anyone having any doubt or any query, any kind of then you please ask that at first, then I will start the class. Anywhere any doubts are there regarding midterm exam? If you are having, then you can ask that at initial stage, and otherwise I will switch to the today's class. Okay, so I hope that I'm quite audible. Any kind of sound problems are there? Anyone please respond. Unmute yourself and please give your response that whether I'm.
Yes, sir, audible.
Okay. Okay. So let me share my screen. Okay. So today primarily we'll discuss regarding a topic that is, as I mentioned, that is advanced counting technique. So it is advanced counting technique, although I hope the screen is quite visible to all of us. It is written recurrence relation. So actually a relation is there in between this recurrence relation and advanced counting technique. So what is advanced counting technique? Make it clear at first. So in some of the application, it may happen that you are counting, and that approach you have to repeatedly apply on that particular problem, and that often occurs in case of any recursive function. So in case of any recursive function, if you are using that, what is the concept that certain kind of calculation repeatedly occurs there, and that kind of counting approach in a repetitive manner we have to continue. So that's why this is a separate counting technique where it is saying yes, certain counting approach is required, but that set of approach we have to repeatedly apply, and that's why it has been separated as advanced counting technique. So this advanced counting technique and this reconciliation, these two are much related. So before this reconciliation, till someone is waiting in the waiting room, let me allow him. So I'm just stopping sharing thing. Okay, so as I was saying, that is certain kind of counting. Oh, this way people joins, then that creates a trouble. Please try to join in time. Otherwise, it creates a lots of problem, because once I go into the presentation mode, again I have to stop and I have to allow you. Okay. So this recurrence relation and the concept of recursive function, they are very much related with each other. So far we have idea about recursive function. Fine. So recursive function, we know what it's a function which we can call, or function can call itself again and again, and one more thing must be there, that is a terminating condition. So once a recursive function we are implementing, that time that recursive function we can represent using a notation, using a functional notation, and that notation it is known as recurrence relation. So recurrence relation is the representation of the recursive function. Fine. So in case of recursive function or recurrence relation, one common approach is that certain kind of dependency. So what kind of dependency? Dependency is there of the function call uh, on its previous function call. So suppose if I talk about factorial function, you can remember that factorial of 5, once you are trying to calculate, it is dependent on the factorial of 4. And factorial of 4, it is dependent on factorial of 3. So that means every time a dependency is there, that is current function call, it is dependent on its previous function call. And this way, ultimately, once it is reaching from 5 to 4 to 3 to 1, and then once it has reached to 1, it is returning the value, because factorial of 1 is fixed, that is known to all of us, that is 1. So that means that once we reach to that base condition, that is known as terminating condition by base condition, it will stop calculating. That concept we are having regarding recursive function. So this way the recursive function works. In this kind of recurrence relation, we will try to represent that dependence in terms of functional representation, which is known as actually the recurrence relation. So in with respect to that recurrence relation, these are the topics we will try to cover. One is concept of recurrence relation, then different kinds of recurrence relation are there. One is linear recurrence relation, another is linear homogeneous recurrence relation, as well as linear non-homogeneous recurrence relation. So our point of concept discuss about this linear recurrence relation. Non-linear recurrence relation we will not discuss, and the different categories of linear recurrence relation again we will discuss in the due course of time. And finally, one more thing we will discuss, that is how to solve a recurrence relation using generating function. So these are the primary topic with respect to this recurrence relation. Now, first of all, make it clear what is recurrence relation and how we can frame a recurrence relation from a recursive function. So recurrence relation is basically what it is saying. It's a representation where certain function call we have to represent depending on its previous function call. So one example, if we consider that this one, which is actually the Fibonacci series, we know 0, 1, 1, 1, 2, 3, 5. That is every two term, previous two term, it is generating the next term, 0 plus 1, 1, 1 plus 1, 2. That way we know that Fibonacci series. So this Fibonacci series corresponding recurrence relation, it is represented like the current term, this fnth term. I said that functional representation is there. So fnth term is dependent on, by it is generated using fn minus 1 and fn minus 2 by combining these two. And that's why fn minus 1th term, if I consider 5, and fn minus 2 term, that is 3. So that's why if I add these 5 and 3, we are getting that it is generating fnth term at a certain moment, certain instance. So 5 plus 3, 8. This way it is generating. And one more thing is important, that it's starting from a certain value of n greater or equal to 2, then only it is starting, because these are known as 0, 1. These are the initial value. That is at first this must be n. So these are can be considered as the base condition. There is f0 equal to 0, f1 equal to 1. These are the base condition, but terminating condition with respect to the recursive function. That means once a recursive relation it reaches to this base condition, it must stop there. No further calculation is there required. So this kind of recurrence relation where repetitive sequence must be there and initial but terminating condition must be there. So these two, if I combine, and then we can frame a recurrence relation which is a representation of the recursive function, we can say this way. So ultimately this recurrence relation, it will help us in counting. Same type of calculation again and again if we are performing, then that approach you can represent using a recurrence relation. So that's why this one is known as a counting approach. And so this recurrence relation where certain term is dependent on its previous terms, definitely. Then one example we have put here, that is factorial function corresponding recurrence relation. Now we all have idea about recursive factorial function concepts. So one thing we have done, just we have put this factorial function. This is the definition in terms of C programming. So we have written, say, factorial of int n. So this is a function definition of factorial, and this is the argument list by parameter list, and then function is having the body. So this portion is the body. So if n greater than 1, it is saying return n into factorial n minus 1, else return 1. So the terminating condition is clearly mentioned. The function should call itself, clearly mentioned. So these two are the definitely important property of a recursive function. And one more property silently is present there, which I must mention here, that is this property. That is an approach to reach to the base condition. That is n minus 1. Because if by mistake if I put here instead of n minus 1 n, although recursive function call is there, terminating condition is there, so this recursive call will never reach to the base condition. So this way it will create a trouble. So that's why three property with respect to recursive function must be there. Then only we can consider that as a recursive function. One is a terminating condition, two are an approach to call itself, and number three, an approach to reach to the base condition. So these three must be there in our recursive function. Now, if this is a recursive function given to us, now look carefully how we are representing this recursive function in terms of recurrence relation. Recurrence relation is a relation where we represent the dependency in terms of the function. So how we are representing that? So the first line, look it carefully, factorial int n, this line we have represent using a dotted syntax dot 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 t of n. So actually we are saying that these functions we are representing in terms of a factorial functions, we are representing in terms of a notation, that is t of n. What is t of n? Now it's a representation of the function, and which represents, t of n actually represents how many time I will call this factorial. Again, t of n represents what? Now t of n represents how many time I will execute this factorial function call. And I am assuming an arbitrary term I have written, t of n. The function it will represent that how many time I will call this factorial function. That is t of n. How many time I will execute this factorial function. So I don't know exactly how many time. That's why I am assuming one expression t of n that will represent. Fine. Then if condition, if you check if n greater than 1, now look it carefully that this is a single line statement. So how many times I can execute this? If I consider this is a single line statement, if that is one time I can execute. So that's why I have mentioned here one. So one means this line I will execute one time according to the way I have written this. If means I can execute this one time. Instead of if I am having a for loop, then I can say that a certain in number of times. But it is a if statement, conditional statement. That's why it's one time. Next, return n into factorial n minus 1. How many times I will execute this n into factorial n minus 1? Now, again, it's a function call. So function call, just like factorial of n previously we have seen here, it is taking in tn time. Now, just because we are changing the parameter n minus 1, that's why we are saying that it will take t of n minus 1 time. If factorial of n takes t of n, factorial of n minus 1, I'm saying it will take t of n minus 1. Why it is? Because I am changing the parameter of the input to the function. So that's why it is t of n minus 1. So previous time it was input n, that's why t of n. Right now what is input n minus 1, that's why t of n minus 1. Now if you ask me that then what is the significance of this n into thing? No, I am considering the entire thing as a function call. N into function call. That means actually our intention is to identify how many times we will execute this entire line. How many times we will execute this entire line. So how many times? It depends on the input n minus 1, and that's why it is t n minus 1. And finally return 1. So it will be again return finally one time. So that's why we have mentioned here one time. So all these execution time, that means how many times I will execute each and every line, we have specified here. Now the recurrence relation is saying that if I combine all these execution, number of executions, whatever we have identified, so that is basically Tn, that will be comprised of all these portions of execution. So Tn, that's why we have mentioned summation of T of n minus 1 plus 2. 2 means basically this one and that one, these two. So T of n, that comprises of two things. One is T of n minus 1, that is the function should call itself kind of execution, and the rest of the two single line statement corresponding to. And when it will happen? Now it will happen whenever it is n greater than 2, greater than 1. And look it carefully that T of n minus 1 plus 2, here is the expression where clearly it is indicating that nth term is dependent on n minus 1th term. Something like factorial 5 is dependent on factorial 4. Something like that. So recurrence relation objective is that. That is represent your function in certain manner so that it represents that your current function is dependent on its previous function. That is current input instance is dependent on its previous input instance. So here it is nth term is dependent on n minus 1. This way it is happening. And it is happening whenever it is n greater than 1. And next line we have done one thing. This 2 we have replaced with a constant a. So 2 we have replaced with a constant a. So that we can do at any moment of time. That is either we are having a constant 2 but 20 but 200. Actually we can easily replace that using a constant variable a I have used here. So I think that again someone is waiting in the waiting room. Let me. Okay, so this way we have framed this recurrence. Yes.
Hello, sir. Sir, beside the if statement, we have written one. Is sir, in every case, beside the if statement, we will take one, or it is because of n is greater than 1, That's why we
No.
have written one.
No, every if statement, if means how many times I can execute that statement. Conditional statement, if the condition satisfied, then only.
Yes, sir.
So that's why it is one. Not that key n value is important.
For every time, in every case, there will be one, right? Whenever
Absolutely.
we will write if. Okay, sir.
Absolutely. So conditional statement we can execute how many times? One time, if condition satisfies or not, accordingly. But iterative statement, by loop kind of statement, we can execute how many times? Many times. If a loop is going on n times, so I will mention n along with the loop. Okay. So when I must take the pointer. So finally we have written that we have identified a recurrence relation something like this: Tn equals to Tn minus 1 plus a, and this is possible when? Now when n is greater than 1. Now also this one is important, that is equals to 1 either when n equals to 0 or n equals to 1. Now tell me that why this one is also important. But this is basically what? Tn equals to 1, it is representing basically what? When n equal to 0 by n equal to 1. Okay, your views please. This is basically representing what? Tn equals to 1. Okay, so this is basically representing the terminating condition or the base condition, isn't it? So once n equals to 1 by n equals to 0, function will return 1. In case of factorial, we know that is known as terminating condition, base condition. So this is happening in case of factorial function. Now let's switch to another function. Like this time my function name is func1 fung1, and certain steps are there. Like she asked me that in case of if it is one time always or not, I said one. Now this time along with if we are having a for loop, fine. So within the for loop certain steps are there, and then outside the for loop one recursive function call is going on there, func n minus 1, and this way we have written this function. So I must suggest you or request you that use your pen and paper and try to identify the individual step corresponding count. That is how many times we can execute these individual step, and then try to frame the recurrence relation from this function fung1. So identify individual stepwise count, that is actually known as frequency of each and every step, and then try to figure it out the recurrence relation of this particular function. Right? So try to do it quickly. I'll wait for 1 or 2 minutes. And if you have done, then give your response. So identify individual stepwise frequency, sum them, and then accordingly try to identify the recurrence relation. I hope that some of you have tried that one, that is individual stepwise frequency you have identified. So the next step is add them, and from that expression specify the recurrence relation, possible recurrence relation. Okay, so any of you wants to share your response? Then please share that. Okay, so I hope that you have identified that stepwise frequency. Fine. So most probably this is the thing you have already done. Fung1, that is the function call corresponding function. That means how many times I can call this function 1. Then if statement, for loop is there, right statement, and func 1 corresponding. Whether this portion is clear to all of us? Whether this portion is clear to all of us? Actually, once I am in the presentation mode,
Sir, why the for loop is n plus 1?
Okay. Okay, good question. Why it is n plus 1? Now look that the for loop is going on I equal to 0 to I less than n. So what is the correct value of last correct value of I?
Say n minus 1.
N minus 1. So whether then only it will come out of the loop?
Yes, sir.
No. Once I value is n minus 1, whether it will come out of the loop? Now it will go on.
So it will execute the statement.
It will execute the step right, and then I value it will be incremented and I will reach to the n. That means last time one more comparison it will happen. What is the I value that time? Now that time I value it will n. So that's why that plus 1 is there. So finally this for loop we will execute n plus 1. Plus 1 indicates that is body it will execute n minus 1 n times. Body it will execute n times. That is it will print a n times. And again the last time the condition once it will be it will not be fulfilled. That is it will become n. That time it will come out of the loop. And that's why this plus 1 is there. So plus 1 indicates the last time checking condition. Last condition, that means using which it will come out of the loop. That's why it is plus 1. And under this for loop, whatever statements it will be there, definitely that we will execute n times. No doubt about that. So the plus 1 means last time condition once it will come out of the loop. That's why plus 1. Fine. So these individual steps, if we can sum, then we can frame the recurrence relation something like this. That is Tn equals to 2Tn minus 1 plus 2n, Tn equals to Tn minus 1 plus 2n plus 2. And that is happening when n greater than 0. And Tn minus 1 plus Bn plus A we have written just because we mentioned that at any moment of time we can replace the constant using a variable. So that's why B by A, these are constant variable. So instead of 2, we have just replaced them, and Bn plus A we have written. And once this condition is failed, that is n greater than 0 is failed, n is equal to 0 but less than 0, then only the function it will be terminated. It will no longer call itself again and again. So that's why we have written 1 once it is less than equals to 0. And that is the terminating condition, again we can say, in case of this particular function. So this way we have represented this function in terms of its recurrence relation. Fine. Now these recurrence relations, all these recurrence relations, if we can frame, actually we have to frame first, either from a function or from a problem statement, and then this recurrence relation we have to solve. And if we can solve this, then ultimately what we can find. Now our objective is that how many times our calculation will go on. That is the thing. So once we can frame the recurrence relation, then our final target it would be that we have to solve the recurrence relation, right? And that we will learn in this particular class. That is how to solve the recurrence relation. Now, one problem we have at this particular slide: determine whether the sequence Fn is a solution of the recurrence relation Fn equals to 2 Fn minus 1 minus Fn minus 2 for n equal to 2, 3, 4, where Fn equals to 3n. So first make it clear that what the question is trying to say. Now the question is trying to say that Fn equals to 3n, this is basically the solution of the recurrence relation, and this is the recurrence relation. We have to check whether this is a solution, of this particular recurrence relation or not. As I mentioned that our primary target it would be that solve the recurrence relation, and that's why if I say that this is a solution, like then you can determine that from this solution ultimately what we can get. Now if I put the value of in 5, then I can identify that f of 5 equal to 15, say 15 number of steps by 15 amount of time, and that is the thing ultimately we have to calculate. That is how many times my function it will take, total number of calculation, how many times it will go on this way. So the solution, if I put a specific value of n, we can determine the total counting value of a certain instance of n. But this time it is asking that this solution Fn equals to 3n, is it a solution of this recurrence relation or not? So simply what we can do, we can put this into the equation and we can determine whether what kind of values we are obtaining. So the recurrence relation, we have to observe it carefully. So the recurrence relation Fn equals to, the right hand side is saying 2 Fn minus 1 minus Fn minus 2. There we have to put the solution. So in the right hand side, you have to put the solution. So if you put the solution in the right hand side, all non-negative integer, yes, that is very important, because otherwise the range we can't determine actually. So in the right hand side, Fn equals to Fn minus 1 minus Fn minus 2. If you put the value of Fn minus 1, so your solution you are saying Fn equals to 3n, so Fn minus 1 it should be 3n minus 1, and Fn minus 2 it should be 3n minus 2. So those values we can put in terms of Fn minus 1 and in terms of Fn minus 2, because it is given that if Fn equal to 3n is the solution, then Fn minus 1 it should be 3n minus 1, Fn minus 2 it should be 3n minus 2, and those values we have simply put, and we are getting that 3n is coming, so that means it is matching with the solution. So this way it is confirming that yes, the given solution is a correct solution of the given recurrence relation. So at any moment of time, different terms we can evaluate from the solution, and we can put that in the recurrence relation, and we can determine whether it is matching or not. So this is one kind of approach which we can apply in case of recurrence relation. Now here the solution we are checking with respect to a recurrence relation. Now different or the reverse approach is possible. Yes. What is that? Now recurrence relation is given, you have to determine the solution. Here solution is also there, recurrence relation is also there, we are validating the solution. Another kind of problem is possible, recurrence relation is given, you have to determine the solution, and that is quite natural problem. So with respect to your say functional representation of the problem, you can determine the recurrence relation, and from the recurrence relation you can find the solution, and from the solution at any particular instance of n you can determine a specific solution value. That is quite possible. Now we will switch to a thing that is linear homogeneous recurrence relation. So basically linear homogeneous recurrence relation is saying this way, that linear homogeneous recurrence relation with degree k and with constant coefficient in a recurrence relation of the form an equals to c1 an minus 1 c2 an minus 2 plus ck an minus k, where c1 c2 ck these are constant, and k is the degree of the uh, linear homogeneous recurrence relation it is saying. Then this c1 ck c1 c2 ck these must be constant, and just because these are constant, then it must be clear to us that this can't be 0. This is not equal to 0. It can't be 0. Its value can be 1 or any other constant, but it can't be 0. And then this an, which is the actually nth term, it is dependent on, clearly you can notice it is dependent on a previous term like an minus 1, an minus 2. That means clearly the recurrence relation property it is maintaining. That is a certain function call, it is dependent on its previous function call, something like that. So one thing I must make it clear that either we can represent these terms like an, but t of n we have seen. Also sometimes we can represent this in terms of a function like f of n, f of n. Fine. So different representations are quite possible to represent this functional representation of a recurrence relation. Fine. F of n, but t of n, but an, like this an. These are same thing, and its degree is saying k, because kth term up to the kth term we are using, that's why its degree is saying k. And with respect to certain boundary condition, which is the initial condition, which is the terminating condition we can say, so these are the certain terminating condition must be there in our recurrence relation. So it is not necessary that many terminating condition possible, one terminating condition must be there. So with respect to factorial, as we have seen that the value once it reaches n equals to 0 by 1, the value returns, it returns 1, that is the terminating condition. Similarly, in case of Fibonacci f0 by f1, they are having initial value of 0 by 1. So those are the terminating condition we can say. So in case of linear homogeneous recurrence relation, the current function call an by fn by tn is equals to a constant into an minus 1. So every time it is dependent on its previous terms, either one term but two term or many term, it is having no effect. So that's why we can also notice that if I switch all these terms to the left hand side, so the terms become something like an minus c1, an minus 1 minus dot 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 equals to finally it is 0. So no constant but no nth term should be there, which that means which can exist in the expression. No that kind of terms are allowed. So that's why we have mentioned these expressions at first. Fn equals to 0. So actually this linear homogeneous recurrence relation representation also we can mention this way. That is Fn means basically that is representing the all the terms we have switched to the left hand side, and then we are making it equals to 0 for all n. So one example we have taken here. Before making this example, that these examples actually will verify one by one. So first one, Sn minus 2 plus Sn minus 4. So is it a recurrence relation, a linear homogeneous recurrence relation? Sn minus 2 plus Sn minus 4. So from the expression we can suggest that actually the dependency is where? That means which term is dependent on whom? That thing is missing. That is Sn equals to, say, if the same expression we write this way, Sn equals to Sn minus 2 plus Sn minus 4, then only we can say that nth term is dependent on n minus 2 and n minus 4. Then it could have been the linear homogeneous. So right now it is not. Fine. So this is not, because the dependency is not there. Nth term is dependent on whom? That is thing not there. Next, number 2. Fn equals to n into Fn minus 2. Is it a recurrence relation? Is it a linear homogeneous recurrence relation? So your views this time, please. Is it a recurrence relation? A linear homogeneous recurrence relation? What is your views, please? Share your views. Okay. So Fn equals to n into Fn minus 2. Look carefully. The Fnth term is dependent on its previous term. Yes, Fnth term is dependent on its previous term. But the important fact is that it is written n into Fn minus 2. But if I go back and to the previous slide, we can notice that an equals to c1 into n minus 1. Yes, that is the previous term. That is also the previous term. So any number of previous term, as we mentioned. But one thing is important, that along with the term, the constant factors are there, but constants are there. C1, C2, these are all constants. But here, in case of Fn equals to n into Fn minus 1, here n is not a constant, it's a variable. So depending on that, that's why we can say that this one, that is Fn equals to n into Fn minus 2, this is not a linear homogeneous. What about the next one, number 3? So now you share your views, please. Number 3 is a linear homogeneous recurrence relation or not? So am I connected or disconnected? Because in case of presentation mode, I can determine that. So please share your views or give your response at least, so that I can think that, or I get an idea that I am connected and you are getting my voice. Is it a linear homogeneous recurrence relation? Okay, so it is not a recurrence linear homogeneous recurrence relation due to these two, because constant factors are there. But in case of linear homogeneous recurrence relation, it's a linear representation of the recurrence relation, where no constant but no nth term should be there. That's why we have written here also Fn equals to 0, that kind of. Only the functional representation must be there. No terms, standalone terms must be there. Okay, next number 4. So it is quite clear that ck minus 5 into ck constant into ck minus 1 plus constant into ck minus 2 ultimately is equal to 0. No constant but no nth term is there. That's why it's a Fn equals to 0 representation. So yes, this is a representation of the linear homogeneous recurrence relation. It is not. So this is a representation of a linear homogeneous recurrence relation. Similarly, Pn equals to 1.1. Is it a constant? Yes. Pn minus 1. Yes, previous term of Pn. So it is again a linear homogeneous recurrence relation, and its order is 1. Its order is 1. So this way, but its order is the fourth number recurrence relation order is 2. The how many terms are there accordingly? The its order is 2. Ck, kth term. So these are the linear homogeneous recurrence relation. So our intention is that how we can solve this linear homogeneous recurrence relation. So quickly we'll check uh, that particular thing, how to solve this linear homogeneous recurrence relation. Before going to that thing, one thing it is mentioned that two types of questions are quite possible. One is solution given, frame the recurrence relation, or recurrence relation is given, identify the solution. In case of this recurrence relation corresponding problem, these two are the thing which we can face. So solution given, frame the recurrence relation. Take this one. Fn equals to 3 into 5 to the power n. Is it a solution? Yes, it's a solution. So it is asking that frame the recurrence relation. Now make it clear that how we are framing. So 3 into 5 to the power n, that 5 to the power nth term, we are saying 5 into 5 to the power n minus 1. And then this 3 into this 3 into and this 5 to the power n minus 1, that we are representing as fn minus 1. So that is becoming 5 into fn minus 1. So exactly that is the recurrence relation we are getting. That is certain nth term is dependent on its previous term in a factor of 5. Fn equals to 5 into fn minus 1. So this way we are making a recurrence relation from a given solution. So this is our solution. Fn equals to, this is a solution given, and from the solution we are identifying the recurrence relation. Fine. Next, and yes, that is also important because a certain boundary value must be there. Otherwise, the terminating condition we can't specify. So this way, one type of question we can solve. Another question is possible, that is recurrence relation is given, you have to identify the solution. So quickly I will discuss one thing, that certain rule is there to solve a linear homogeneous recurrence relation, and the rule is that using characteristic equation we can solve that. So I must specify the rule quickly because that is very easy. The first thing is that you identify or you specify the characteristic equation first. How to frame the characteristic equation? Now look it carefully. Qk plus 2qk minus 1 minus 3qk minus 2, all these terms at first we are initializing in terms of r to the power of k, r to the power of k. So this qk we are replacing by r to the power k, qk minus 1, r to the power k minus 1. So this way r to the power k plus 2 r to the power k minus 1 minus 3 r to the power k minus 2 minus 6 r to the power k minus 4 equals to 0. So that is the linear homogeneous recurrence relation characteristic equals to 0. So every term in power of to the power of r we are replacing. If it is given k, then r to the power k. If it is given k minus 1, r to the power k minus 1. Then identify the minimum r power term. Identify the minimum r power term. What is that? R to the power k minus 4. And divide the entire expression by that. So r to the power k by r to the power k minus 4. This way, all the terms we have divided by r to the power k minus 4. And we are getting this r to the power 4 plus 2r cube minus 3r square minus 6. And that is known as the characteristic equation. That is known as the characteristic equation. So r to the power 4 plus 2r cube minus 3r square minus 6. This is the characteristic equation. And our objective should be that identify the characteristic root from this equation. So this represents that the kth order linear recurrence relation, and then from that recurrence relation find the root. Step 2 is saying find the root. So step 1 saying find the characteristic equation, step 2 is saying find the characteristic root. So once you can determine the root, then corresponding those roots, certain rules are there, that is coming under step 3, case 1 and case 2. We will see that with respect to some example, and then finally with respect to step 4 we will determine certain value or solution. So this is the rule of solving linear homogeneous recurrence relation. So with respect to an example, quickly we will check the rule. So one example, just I am considering quickly, this is the Fibonacci series corresponding recurrence relation, where we will apply the rule. So first we have framed the characteristic equation, r to the power n minus r to the power n minus 1 minus r to the power n minus 2. And then we are dividing the entire expression by minimum term, r power term, r to the power n minus 2, and we are getting that this result is coming. And from this result, we are determining the root. The roots are coming this way, minus b plus minus root over b square minus 4ac by 2a. And two roots we have identified. So now the step 3 is dependent on this root value, whether the roots are same or roots are different. So that's why we can observe that roots are different. So if the roots are different, then case 1 is applicable. So if the roots are different, case 1 is applicable. If the roots are same, case 2 is applicable. So case 1 corresponding rule we have applied, and we are getting this a1 into c1 to the power n plus a2 into c2 to the power n. So actually what it is saying, that if I go back quickly to the previous slide, what is the rule 1 is saying? That if k number of distinct roots are there, then the possible solution of this equation is a1 into c1 to the power n, where c1, c2, these are the roots. One of the root we have seen, two roots c1 and c2 in this particular problem we have observed. So how many roots we are determining, that we can put accordingly this approach of k number of distinct roots. So a1 into c to the power n, a2 into c to the power n. So just because two roots right now we have identified, that's why these two terms only we have considered. But if it is k number of roots, then kth term we have to consider. So this way we have applied this case 1 rule here, and this is the expressions we are getting. Finally, step 4 is saying that these constant a1 and a2, using the boundary condition, we have to identify. What is the boundary condition? If n equal to 0, then it is 0. If n equals to 1, then it is 1. So these two are the boundary condition. So use this boundary condition and determine the value of a1 and a2. So two expressions we have written. These are the expressions after applying the boundary conditions we are getting. And from these two expressions, we have identified the value of constant a1 and a2. And then those values we have applied in this expression, and we are getting the final solution of this given recurrence relation. Fine. So this is the approach of solving this linear homogeneous recurrence relation. Fine. So I have taken 3 minutes extra. So just to complete this particular thing, and I must request that please go through this slide and go through this type of problem, and you have to solve this type of recurrence relation during the final semester. Fine. So today is that much. Next class we'll discuss the rest of the thing. Okay, fine. Thank you. And I must post the attendance link, and so that you can keep the attendance.
Send the PDF also, sir.
Yes.
Send the PDF also in the group.
Sure, definitely. Okay, so all you must ensure your attendance. Thank you. And requesting you to please, after giving your attendance, leave the meeting so that next class I am having in this particular link as well, so that no class will be there. Thank you.